Welcome back to Differential Calculus. Previously, we've been looking at this idea of the derivative. We've looked at one of several applications of the derivative, namely that we can use it as part of the process of writing the equation of a tangent line. In this video, I want to start looking at some of the more powerful tools that we can use so that we don't have to use that limit process in order to find the derivative each time. There are two tools in particular I want to look at. The first one is the idea of linearity. The second one, probably a little bit more powerful, the power rule. Let me get my head out of the way and we'll get into that. We've already worked with the derivative of a function in the past. So if we have a function f of x, the derivative of f of x is another function, which we've been denoting as f prime of x, and it's defined using this limit definition. I've also mentioned this other notation that we can use for the derivative, df over dx, which is based on the slope formula, change in y over change in x, and if we set y equal to the f of x, we could equally write that as change in f over change in x. Let's make that thing in the denominator there look like an x. And then we change those deltas to these d's to get the derivative. This other notation is from, or more powerfully used as, what's sometimes called the differentiation operator. We can write d over dx square brackets f of x is equal to f prime of x. Vocabulary here: derivative and differentiation. This is something that doesn't feel like a big deal, but it is a point where a lot of students get confused on the vocabulary. Differentiation is the process we are going to start working with in this video and continuing on for several more videos that will allow us to figure out, based on a function we are given, what does the derivative of that function look like. So differentiation finds a derivative. Every now and then I will hear a student talk about derivation because it sounds like that should be what gives you the derivative. And I want to emphasize right now, derivation is the algebraic process of bringing equations together to find a solution. You use that in applied problems in algebra, in physics, and in other applied mathematical sciences. Derivation has nothing to do with calculus. So that's a place that I want to make sure that you are careful and precise about vocabulary. The process of finding the derivative is called differentiation, and it's based on the differentiation operator that I'm now standing in front of. So let me get myself back out of the way so that we can look at this a little bit more closely. Differentiation is an operator. An operator is a rule which maps one function to another function. And that name in and of itself, that definition should be very familiar to you. A function itself is a rule which maps one number to another number. Operators do to functions what functions do to numbers. So we are going to be looking at the differentiation operator. There are two rules that I want to look at with the differentiation operator. For the sake of time, I'm just going to tell them to you, which is a little bit boring. If you're really interested, you can in fact prove these rules. You can use the limit definition of the derivative, which I just scrolled off the screen, to verify that these properties must be true. It's kind of boring, to be honest, so for the sake of time, I'm not getting into it. But if you are curious, it's available. I'm happy to provide resources showing you how some of them work. The first rule is linearity. I've mentioned linearity before. When things are linear, they make us happy because they allow us to do a lot of stuff that we want to do. For functions, f of x and g of x, and for constants, a and b, the derivative d dx acting on the linear combination a times f of x plus b times g of x is actually going to distribute. You're going to get a times df dx plus b times dg dx. Or if you prefer, a times f prime of x plus b times g prime of x. The second rule is the power rule. If there is one rule for differentiation you know, it should be this one. All right, I'm going to say for an integer n, but I'm going to be honest. This actually does work for any real number n. And the power rule tells us that the derivative, d dx, of x to the n power is n times x to the n minus 1 power. So whatever power you have, you multiply in front of the x by that power, and then you reduce the power by 1. So for example, if I want to take the derivative of x to the 4th power, my n is 4 in this case, that comes in front. Then I have x to the 4 minus 1, which is 3. The derivative of x to the 4th power is 4x to the 3rd power. And no, you don't have to write that step in. If you just go straight immediately to the conclusion, that is perfectly fine. If I have something like the derivative of 1 over x cubed, well, properties of exponents, 1 over x cubed is x to the negative third power. Now my n is negative 3. I put the negative 3 in front. I multiply by x to the negative 3 minus 1, which is negative 4. And sure, why not? Use properties of exponents to rewrite that back as a fraction. When I'm doing this on my own, it's 50-50 whether I'm going to write that step in. Something this straightforward, I probably would not. But when they get more complicated, and this is just one piece of what's going on, I find writing that step is more convenient. From that step, I will always write this step out. And then depending on the application, depending on what I'm trying to do with it, I may or may not switch it back to writing it as a fraction. So as you're writing things out, if it helps you to write out all of those steps, go for it. If you are comfortable skipping a couple of those steps, that's fine. If you're not sure which of these two forms is the correct way to write the answer, well, neither am I, honestly. It depends on the situation. It depends on what you're doing. Or do you have more work to do on the problem after this, or is that the end of the road for you? I said when I wrote down the power rule that it only worked for integers, but it does work for any real number. So if I want to take something like the derivative of the square root of x, well, properties of exponents. The square root of x is x to the 1/2 power. My n is 1/2. One half x to the negative 1/2. And we can keep going from there. That negative power pushes the x to the denominator, and the 1/2 power is just a square root. So the derivative of the square root of x is 1 over 2 times the square root of x. I think with this one, it's time to start looking at some of the value of this process. I mean, sure, it's honestly, I think it's a fun algebraic toy. I will sit around and play with derivatives like this when I'm bored, just for something to do to occupy my brain a little bit. But I'm weird. There is a purpose. It's not just we can do this so we can do it. This is the tool for finding a derivative, and all of the tools that are useful for derivatives will still apply. The only one we have right now is that we can use derivatives to write tangent lines, and that absolutely does still work. So we just saw in that example, for the function f of x equals the square root of x, the derivative f prime of x is 1 over 2 times the square root of x. With that information in hand, we might want to write the equation of the line tangent to y equals f of x when x is equal to 4. And we absolutely can do that. We know that to write the equation of this line, we need to know what happens to y when x is 4. Well, in this case, that's just the square root of 4, which is 2. So the point 4, 2 is a point on the line. We also need to know the slope of this line, which is the derivative of the function at the point in question. Well, since we have that formula for the derivative, 1 over 2 times the square root of 4, which is 1/4. We have our point, we have our slope, we can go. Y minus the y coordinate is equal to m times x minus the x coordinate. Rearrange a little bit to clean up. And there is the equation of our tangent line. For the sake of time, I'm just going to leave it there. If you're interested, I encourage you, go into Desmos or something like that, graph the function, graph the square root of x, graph the tangent line, 1/2 x plus 1, and zoom in near the point 4, 2. You should see that the equations line up perfectly. If I can hit the right button, let's take a look at one more example. F of x is 5x cubed minus 7x squared plus 8x minus 27. This is where that property of linearity is going to come in and join us in our discussion of the power rule. If I want to take the derivative of this function, I can notice that this function is made up of a bunch of constants multiplied by a bunch of variables. And well, this last one is a little bit interesting. But again, going back and thinking about properties of algebra, x to the 0 power is 1. So if we insert that x to the 0 power right there, we can get through this without any issue. I'll also point out while I'm thinking about it, x by itself is x to the first power, and that will also be useful to us because we need to have the powers explicitly written out. But using the linearity, this is going to be 5 times the derivative of x cubed minus 7 times the derivative of x squared plus 8 times the derivative of x to the first. I'm running out of room. Let me just slide this over. That's why I love teaching on this tablet, because I can just give myself a little bit more room whenever I need it. All right. Mostly all fits on the screen. Good enough. The first couple are very straightforward. The derivative of x cubed, bring the 3 in front. 3 minus 1 is 2, 3x squared. Likewise, the derivative of x squared is 2 times x to the first. The derivative of x to the first is 1 times x to the 0. And the derivative of x to the 0, just continuing to follow my power rule, is 0 times x to the negative 1. Well, that last term is pretty convenient, right? Multiply by 0, I don't care what's going on with anything else. This is just 0. Earlier than that, the x to the x to the 0 term is just 1. So that's another thing that's going to go away. And then if I remember that I don't have to actually write out an exponent of 1 when it shows up, I get that f prime of x in this case is 15x squared minus 14x plus 8. There we have it. So I have two problems for you to look at, which are closely related to each other. For the function f of x equals 9x to the fifth minus 45, I would like you first to write out the derivative function, f prime of x. Then when you have that, I would like you to write the equation of the line tangent to the graph y equals f of x at the point when x is equal to 1. Take a couple of minutes, see what you can do with that, and I'll see you in the next video.